Good afternoon to all of you. I hope everyone has downloaded the software successfully. So in this session, you can do the hands-on. So you can follow the same procedure that I have followed. So you can open your software. So first I would like to share my screen. So all the participants, you can open your software. So you can see I have downloaded the software on the C drive. So I would like to open my C drive. And this is the Device Studio 2022A folder. I would like to open this folder. And then you can open the bin folder. And drag and drop. Then you will find this Device Studio application file. So you can open the C drive. Then open this Device Studio 2022A folder. Then you can open the bin folder. Drag and drop. Then you will find this Device Studio application file. So you can open this Device Studio application file. Double click on this file and then it will be open. So I hope everyone is following the same procedure and that I have showing. So you can click on this create a new project. Then you can click on this OK. And you can enter the name of your project. And you can select the location where you want to save your project. And then you can click on this save option. So I hope everyone has created their project. And they got this interface. So once you created the project, then you can go to the file option and then you can select this import option. So either you can create your material, crystal structure, molecular structure, or either you can import from this local database or online database. So I would like to import from this local database. So you can select this import option, then import local, and then go to this location, C drive, Device Studio 2020A. Then you will find this material file, and this material file will be there. Here you can see this is the Device Studio 2020A folder, and in this folder you will find this material folder. You can select this material folder and then you will find this database. So you can select this 3D material, then go to this layer material, and then you can select this boron nitride. So you can select this 3D material, then go to the layer material, then you can select this boron nitride. Once you selected this boron nitride, then you can click on this open. I hope everyone has imported this boron nitride from their local database. So for importing this boron nitride, you can select this file option, go to this import option, select this import local, then go to this C drive, open this Device Studio 2020A file, then you will find this material file. You can select this material file and then you will find this material database. And for the boron nitride, you can select this 3D material, select this layer material, and then you can select this boron nitride. You can select, then you can click on this open.
Sir, how do you freely rotate this structure?
Here you can see this is the 3D viewer rotation mode. So you can select and then you can rotate. Or without selecting this, you can right click on the mouse and you can rotate like that. So first I will show you the DFT density function theory calculation, and after this I will show you the density function perturbation calculation. So for the DFT you can select this simulator, select this rescue, and then you can select this self-consistent field calculation. You can select simulator, select this rescue, then you can select this self-consistent field calculation. And here you can see this is the SCF calculation for this boron nitride. So you can select the parameter as per your need. So you can take the default parameter, because as much as you increase the parameter, then it will take more time to calculate the properties. So it is better to take the default and then generate their file. So here you can see this is the basic setting, shimmering sigma, and this is the resolution. And in the method you can see this is the Rayleigh space, and this is the linear combination of atomic orbital. So first I can select this Rayleigh space, and this is the exchange correlation, LDA, GGA, meta GGA, hybrid function is also there. So you can select this LDA, and this is the K-point sampling, and this is the iteration control, tolerance, charge density, total energy. So if you get this interface, so you can click on this cancel. You can download this license file. You can download. Here you can see I have already downloaded. And after downloaded, you can copy this file and then go to this C drive. Here you can see this is the C drive. Then you will find this in Device Studio 2020A file. You can open this file. You can open this bin file and you can paste here. You can paste here. So for simulating this boron nitride, you can select this simulator, select this rescue, go to the self-consistent field calculation, and here you will take the default parameter, and then you can click on this generate file. So you can add some spintronics application, like this is the collinear spin you can add. You can add this collinear spin. And then you can click on this generate file. So once you generate the file, in the project explorer you can see the scf.input file and atom.xyz file has been generated. So you can select this scf.input file, right click, select this run option to run this job. So to run this scf.input file, select this file, right click, select this run option, and here you can select this run option. In the job manager you will find the scf.input file is in the running condition. So you can minimize this interface. You can select this scf.input file, right click, select this run option to run this job, and then you will find this in the job manager. You will find the scf.input file is in the running condition, and here you can see my scf.input file calculation has been finished. And once your calculation will finished, you can select this simulator. Again you can select this rescue. Then you can go to this analysis. Select this simulator, rescue, then you can select this analysis. And here you can see this is the density of state, band structure, Molkin population, potential. So you can double click on this density of state and it will be selected. Here you can see calculation selected 1, density of state. And here you can see this is the density of state parameter. So you can define some k point sampling so that their output graph will be plotted. So you can select n1 is equal to 3, n2 is equal to 3, and n3 is also 3. You can select. And if you want to calculate projected density of state, local density of state, so you can select anyone. So I would like to select this local density of state. So you can double click on this density of state, then it will be selected. Then in the density of state parameter, you can define n1 is equal to 3, n2 is equal to 3, and n3 is also equal to 3. Once you selected this density of state, if you want to calculate more analysis, so you can select this band structure, double click on this band structure, then it will be also selected, and then again you can click on this band structure, and then you will find this parameter. So if you are getting any error, so you can drop on the WhatsApp so that my technical team will help you. After selecting this parameter, you can click on this generate file so that their input file will be generated in the project explorer. So in the same way, you can run this input file local density of state band structure dot input file. You can select this local density of state, right click, select this run option. You can select this local density of state dot input file, right click, select this run option, and then you can select this run option to run this job. So after running this local density of state, in the job manager you will find the local density of state dot input file is in the running condition. So in the meantime, you can also run this band structure dot input file in the queue condition. Select this file, right click, you can select this run option. You can select this run option to run this job. I hope everyone is getting their output after running this simulation. And if you are getting some error, so you can send the message on the WhatsApp group so that my technical team will help you. In the job manager, you can see all the calculation has been finished and their output has been generated. So to show the output file, you can select anyone. You can select this rescue log.output, right click, select this open containing folder so that you will find the location of this project. You can select this rescue log.output folder, select this open containing folder, and then you will find the location of the project. Here you can see this is the location of my project and this is the result folder. Again, you can open your device studio, select this simulator, you can select this rescue and then go to the analysis plot. So for the output visualization, you can select simulator, select this rescue, go to the analysis plot, and then you need to select your file, whatever location you have saved. Here you can see this is my project. You can open the file. Then you will find this boron nitride file. You need to open again this boron nitride file. Then you will find this rescue crystal file. Again, you can select this result folder, and then you will find this output. So for the output visualization, you can select simulator, go to this rescue, select this analysis plot, and then you can locate your project. And then we can open this result folder. You will find this output file, and you can select any file, like this is the band structure file, real space density, this is the density of state, this is the local density of state, and this is the potential, real space potential. So first you can select this band structure, then you can click on this open. You can select any output folder, like this is the band structure, then you can click on this open. So I hope everyone is getting their output graph, band structure output graph for this boron nitride. So this is the band structure for this boron nitride. Here you can see this is the conduction band 0 to, this is the conduction band, and this is the valence band, and this line is Fermi energy. Conduction band, valence band, this is the Fermi energy. In this spin type you can see this is the spin up. You can select this up, and then you will find this up down both. So you can select anyone, like this is the spin down, and this is the spin up and spin down both calculation. So this is the band structure output. In the same way you can visualize their local density of state. So you can go simulator, select there this RESCU, then go to the analysis plot. Again you need to locate this project. You can open this result folder, and here you will find this local density of state. You can select this local density of state. You can click on this open. This is the 3D view of this local density of state for this boron nitride. In the draw model you can see this is the 3D. If you want to show the 2D, so you can select this 2D, and this is the 1D. So 3D, 2D, 1D view is also possible. This is the 2D, and in the type you can see this is the spin up. If you want to show the spin down, so you can select this spin down, and here you can see this is the average direction along x-axis, y-axis, z-axis. So any axis you can select, and you can show their data. And this is the 1D. So this is the local density of state. And if you want to export your raw data, so here you will find this export option. So this is the export option, and here you can select the format, any format you can select, and you can choose the location, and then you can click on this save option, so that you can easily export your raw data in any format. I hope everyone has done this density of state, density function theory calculation, and they get their output for the local density of state and band structure. So in the same way you can calculate the density of state, band structure, local density of state, projected local density of state of any material or any molecule. Either simple structure or complex structure. You can follow the same procedure, and then you will get their output. So this is the density function theory calculation. And for the density function perturbation theory, again you can select any material from this database, or either you can create from the crystal builder, molecule builder. So either crystal builder you can create, either molecule builder you can create. So again, you can select this import online option or import local. This is the import local, and this is the 3D material. If you want to study the semiconductor, so here you can see this is the semiconductor material database, and you can select any materials. So here you can see this is the aluminum arsenide. So you can select this aluminum arsenide, and then you can click on this open. So for this aluminum arsenide, you can select this 3D material, go to this semiconductor, and then you will find this aluminum arsenide. You can select, then you can click on this open. So for this aluminum arsenide, if you want to import this aluminum arsenide, go to the file option, select this import option, then select this import local, and then you can select this 3D material, select this semiconductor. On the top you can see this is the aluminum arsenide. You can select, then you can click on this open. And if you want to make a supercell, but for the supercell, as much as you increase the number of atoms, then it will take more time to calculate the properties. So it is better in this session you can perform with this default parameter as much as less number of atoms. And after this session you can do with any complex structure, and you can do their simulation. And then if you are getting any errors, so kindly you can drop the message from the WhatsApp group, then either me, either my technical expert will help you. So I am not going to make any complex structure. I am taking this default parameters. Total number of atom is 2. And then for the DFPT, you can select this simulator, select this RESCU, and then go to the DFPT. So for the density function perturbation calculation, you can select simulator, select this RESCU, and then go to this density function perturbation theory. You can select this, and then this interface will open. So here you can see this is the DFPT calculation, and this is the basic setting. In the task you can see, you can select this, and then you will find this calculation like phonon band structure calculation, phonon density of state calculation, phonon band structure and phonon density of state calculation, optical property calculation, Raman properties calculation. So you can select this phonon density of state calculation. In the task you can select this phonon density of state calculation. This is the sigma sigma resolution, and this is the SCF method real space. This is the exchange correlation LDA. You can take default parameter, you can see, and this is the SCF parameter calculation, and this is the DFPT parameter. In the DFPT method you can see this is the Sternheimer, and this is the Chebyshev filtering. So I would like to select this Sternheimer. This is the basic settings. This is the spin toy, and this is the phonon density of state parameter. Here you can see this is the Q point sampling N2 N3, so that their data will be plotted. You can take N1 is equal to 3, N2 is equal to 3, and so you can define this Q point sampling. So after defining the parameter, you can click on this generate file. In the task, you can select this phonon density of state. You can define their parameter. In the phonon density of state, you can define N1 is equal to 3, N2 is equal to 3, and N3 is also 3. So after defining, you can click on this generate file. So once you click on this generate file, in the project explorer you can see the scf.input file, dialectic.input file, phonon.input file, and phonon density of state.input file has been generated. I hope everyone has generated this scf.input file, dialectic.input file, phonon.input file, phonon density of state.input file, and atom.xyz file. If you want to show the script for this scf.input file, so first you can select this scf.input file, right click, select this open with, and this is the script for this scf.input file and for this aluminum arsenide. In the calculation type you can see this is the self-consistent and this is the location shape path, this is the domain, and here you can see this is the neutral atomic database LDA. Here you can see this is the aluminum and this is the arsenide. So first you need to run this scf.input file. Select this scf.input file, right click, you can select this run option, then you can select this run option to run this job. So you can select this run option to run this job. In the job manager you can see the scf.input file for this aluminum arsenide is in the running condition. In the same way, you can run all the input parameter. First you need to run the SF input, then you need to run this dialectic.input. You can run then phonon.input, then you can run this phonon density of state.input file. You can select this dialectic.input file, right click, select this run option to run this job. So similarly, you can select this phonon.input file, right click, select this run option to run this job. Here you can select this run option. And then you can select this phonon density of state.input file. You can select the file, right click, select this run option. Here you can select this run option to run this job. In the job manager, you will find the scf.input file calculation has been finished. The dialectic.input file is also finished. And the phonon.input file is in the running condition. So you can wait till the calculation finished. So once their calculation will finish, their output file will be generated. So for the DFPT calculation, you can select any material, and after selecting the material, you can select simulator, go to the rescue, select this DFPT, then you can define the parameter. In the task, you can select any parameter like phonon band structure, phonon density of state, phonon band structure and phonon density of state calculation, optical property calculation, Raman property calculation. So any parameter you can select, you can define their parameter. This is the iteration control, density matrix, charge density, total energy. You can define their method, Stern, Eimer, Chebyshev filtering. This is the basic settings, spintronics application, and this is the phonon density of state parameter. So you can define their parameter, then you can generate their file. So once you generate their file, first you need to run the scf.input file. Then you can run this dialectic.input file. Then you can run this phonon.input file. So from the top to bottom, you can run all the input file in the queue condition, and then you will find their output. So once their calculation finished, their output will definitely generated. In the job manager, you can see all the calculation has been completed and their output has been generated. So for the DFPT output file, like this is the phonon density of state. And here you can see this is the phonon density of state. If you want to plot their graph in the MATLAB, Then simply you can click on this open with, and here you can write the command. You can write this command for the phonon density of state. You can see this is the command for plotting the graph. You can write this command and you can plot there. First you need to save this file. You can plot the graph in any third party software like Origin, MATLAB, SCI Lab. So any third party software output folder has been generated. So in the output folder you can see, here you can see, and this is the output folder that has been generated in the text format. So this file format you can import in any third party software and then you can plot their graph. Because I have the MATLAB, so I have written this command. I need to save this file and again I need to run this file. So in a very quick time it will get their output graph. Here you can see the output graph has been plotted. So you can open your MATLAB from this browse option. You can locate your project into the MATLAB. Here you can see this is my project. This is the project. You can select your project location. This is the project. Then you can click on this select folder. And here you can see this is the boron nitride output folder. And this is the aluminum arsenide output folder. So you can select this file. Then you will get this RESCU DFPT file. Again you can open this file. And here you can see this is the aluminum arsenide phonon density of state output file. So you can double click on this phonon density of state and then you will find their plot. Like here you can see this is the phonon density of state with respect to energy. This is the phonon density of state for this aluminum arsenide. Like any material you can select. So you can take any example to calculate the properties. I am taking metal oxide. And here you can see this is the zinc oxide. So this example I have taken. And for their simulation, you can select simulator. Select this RESCU. And this is the DFT, density function theory. And this is the density function perturbation theory. So any method you can apply. For this DFPT, you can select this DFPT. Then you will find this parameter. Like this is the basic settings. In the task you can see this is the phonon density of state, phonon band structure and phonon density of state, optical property calculation, Raman property calculation. So you can select any one. So I would like to select this optical property calculation. You can define their simmering sigma, resolution, SCF method, exchange correlation, LDA, GGA, and this is the K point sampling. And this is the iteration control. Here you can see this is the SCF parameter, tolerance, charge density, total energy, maximum SCF steps, mix method, mix variable, mix history. And this is the DFPT parameter. In the DFPT method, you can see this is the Sternheimer and this is the Chebyshev filtering. So any method you can select. And this is the basic settings. Here you can see this is the oxygen and this is the zinc and they're double zeta polarized. This is the spintronics application and this is the optic and their parameter like damping factor, E-field direction. So as per your need you can define, and after defining the parameter you can click on this generate file. So first you can import this zinc oxide from this local database. Like you can go to the file option, select this import option, select this import local, and for the zinc oxide you can select this 3D material, select this metal oxide, drag and drop. You will find this zinc oxide. Go to the 3D material, metal oxide, then you will drag and drop, then you will find this zinc oxide. You can select, then you can click on this open. So once you click on this open, then this zinc oxide will be imported in your device studio. So after importing this zinc oxide, select this simulator, select this rescue. Any parameter you can define as per your need. This is the DFT, this is the DFPT. So I would like to select this DFPT. In the task, you can define the parameter as per your need. Any parameter you can define, like this is the optical properties calculation. You can define their parameter, basic setting, iteration control, basic set, spintronics application, optic. This is the optic parameter, damping factor and E-field direction. So after defining the parameter, you can click on this generate file. So once you click on this generate file, then this input file will be generated in your project explorer. So here you can see this is the scf.input file, dielectric.input file, phonon.input file, optical.input file, and this is the atom.xyz file. So here you can see this is the scf.input file. If you want to show their script, you can select this file, right click, select this open with, and here you can see this is the script for this zinc oxide. What parameter we have defined? Here you will find this is the oxygen, this is the zinc, and this is the oxygen neutral atomic data, like double zeta polarized. So first you need to run this scf.input file. Then you can run this dielectric.input file, because in the dielectric.input file you can see it will take the output from the SCF calculation. Here you can see it will take the output from the scf.mat file. So first you need to run the scf.input file. Then you can run this dielectric.input file. Similarly, you can run from the top to bottom. This is the phonon.input file, and this is the optical.input file. In the atom.xyz file, you can see right click, select this open with, and this is the zinc, and this is the oxygen and their Cartesian coordinate point. This is the Cartesian coordinate point. So I have run all the input in the queue condition. Here you can see the scf.input file has been completed. And for the parameter, what parameter you need to define? You can visit our official website nanoacademic.com, and on the bottom of the page you will find this documentation and tutorial. So you can select this document and tutorials, and here you can see this is the Nano Academic documentation. You can select your product, like this is the nanodical for the atomic quantum transport simulator, DFT and NEGF, and this is the advanced version of this nanodical plus, and this nanodical plus is written in Python and Fortran, and this nanodical is written in MATLAB and C. This is the RESCU for the large scale Kohn-Sham DFT calculation, DFT and DFPT, and this is the advanced version of this RESCU. This is the RESCU plus. This RESCU is written in MATLAB and C, and this RESCU plus is written in Python and Fortran. And this is the QT for the spin qubit devices. So you can select any product, like this is the RESCU, and then you will find all the details, like this is the introduction, installation, getting started, tutorials, input reference. So this is the introduction about this software. and this is the installation, and here you can see this is the getting started. This is the input file format. Here you can see this is the pseudo potential, and all the theory is there. So whenever you get the time, so you can kindly visit our website, and then you will find all the details regarding this software. And here you can see, and this is the for the output file. And also you will find this tutorial point. Here you can see this is the tutorials, and here you can see this is the SCF calculation, density of state calculation, band structure calculation, atomic orbital calculation, and this is the structure relaxation. And also you can see this is the result, plot result. So whenever you follow the procedure, then definitely you will get their output. In the job manager, you can see the SCF and dielectric.input file has been completed, and this phonon.input file is in the running condition. So in the meantime, if you want to import material from online or local database, so here you can see this is the import local option, and this is the import online option. If you want to import from the online, so here you can enter the chemical formula. Any material you can select, like this is the SIU, and then you can click on the search option, and here you can see this is the SI606, and this is the space group. So any material you can search, like if you want to search zinc oxide, so this is the zinc oxide. You can click on this search option, and here you will find this various zinc oxide with the various combination, and here you can see this is the various space group. So as per your need, you can select zinc oxide, and then you can easily select this add option to build in this device studio. Like if you want to add this one, so you can click on this add option, and then it will be added on your dashboard. And if you want to delete some undesired atom from this structure, like if you want to delete these atoms, so right click, draw the rectangle, select the atoms, then you can press this delete atoms. This is the delete atoms, and here you can see the atom has been deleted. Similarly, if you want to delete single atoms, so you can select the atoms, select this delete atoms, so that it will be deleted. So either single, multiple, any atoms you can select. For the select, you can right click, select the atoms like that, and then you can press this delete atom. And if you want to replace any atoms, like here you can see this is the oxygen, and this is the zinc. Here you can see in the properties, you can see this is the zinc, and this is the oxygen, and their XYZ position. So if you want to select this zinc oxide, and you want to replace this with another atoms, so here you can see this is the replace atoms, and then periodic table will open. So from periodic table you can select any atoms. So any atom you can select, like this is the chlorine, any atom, like this is the phosphorus, sulfur, aluminum. So I would like to select this aluminum, then you can click on this OK. Here you can see the aluminum has been replaced. This is the zinc, oxygen, and this is the aluminum. So in this way you can replace any atoms, or if you want to delete, so right click, draw the rectangle, select the atoms, then you can click on this delete atoms, then it will be deleted. And suppose if you want to add more atoms, if you want to add an atom between these two atoms, if you want to add, draw the rectangle, select the atoms, and here you can see, and this is the add a new atoms. Add new atoms. You can select this one, and here you can see default oxygen atom has been added. But if you want to change this oxygen with another atoms, select the oxygen, go to the replace atoms. Any random position you can add. Like if you want to add here, so you can, one second. You can see this is the add a new atoms. You can select add atoms. You can select any atoms. Like this is the aluminum. Click on OK, and anywhere you can select. Like if you want to add here, you can see it has been added. Definitely it will affect your result, because every atom has their own properties. So when you will add the atoms, then their property definitely changes. And if you want to move this atom at any position, here you can see this is the move atoms, and here you can see this is the transition along XYZ position, unit cell vector, XYZ position, unit cell vector, screen view. So any view you can select. So either left, right, top, bottom you can select, and you can move like that. So like that you can move the atoms at any position. And suppose if you want to make the bond between these two atoms, so here you can see this is the recalculate linker bond. So you can select, and it will make the bond between these two atoms. This is the covalent bond. In the job manager, you can see all the input calculation has been finished. Again, to plot the graph, you can select this optical dot input file. So for plotting the graph, you can select this optical dot input file. Right click, select this open with. Again, you need to write the command for plotting the graph in the MATLAB. RESCU. If you are plotting the graph, you can enter the location where the project has been located. You can write the location, output location of this optical dot input file. Here you can see this is the zinc oxide, this is the result folder, and here you can see this is the optical dot mat file. So this location you can enter in this position. You can write this script, then you can save this input file. You can save this file, and again you need to run this optic dot input file. So in a very quick time, it will plot their graph in the MATLAB. You can see the data has been plotted. Here you can see the calculation has been completed. So for plotting the graph, either optical, Raman, phonon density of state, you can open the file and you can write the command rescue /p, and you can enter the location. Like this is the optical location, optic.mat file, and for the phonon you can enter phonon.mat. For the band structure you can open phonon under space band structure bs.mat, and for the density of state phonon dot density of state.mat, and for the Raman here you can type Raman.mat, and then you can save the input file, and again you can run this input file, either optical, Raman, density of state, phonon density of state, and then in a very quick time you will get their output in the MATLAB. So here you can see this is the zinc. You can see this is my project, and in my project you can see here you can see this is the boron nitride. Here you will find this boron nitride. This is the aluminum arsenide file. Here you can see this is the aluminum arsenide. This is the zinc oxide, and here you can see this is the zinc oxide file, and here you can see this is the .szw file. So this file output file has been generated in the MATLAB. So you can open this zinc oxide file. This is the result folder, and in the result folder here you can see, and this is the zinc oxide plot. So different plot has been plotted. So this is the optic plot for this dielectric. Double click on this file, and here you can see this is the dielectric permittivity for the real and for the imaginary. So this is the real and imaginary part of this dielectric permittivity for this zinc oxide. Here you can see this is the energy, and this is the real, and this is the imaginary. So in the same way you can show this graph. Double click on this graph. This is the IR intensities, and this is the IR and infrared intensity for this zinc oxide with respect to energy. And here you can select this file, and here you can see this is the photon energy loss function. This is the photon energy loss graph with respect to energy, and this is the refractive index. This is the refractive real and imaginary refractive index for the zinc oxide with respect to energy. I hope everyone is get their output plot for this zinc oxide. This is the zinc oxide optical property calculation. So either you can run through this graphical user interface, or if you want export in the writing the script, so either you can write the script in the MATLAB, because as you know this software is written in MATLAB and Python, MATLAB and C. This RESCU is written in MATLAB and C, and RESCU Plus is written in Python and Fortran. So if you are expert in writing the script, so you can write the script, and then you can do the simulation in this MATLAB through the command line interface. Like here you can see I need to generate an input file. This is the import online option. If you want to import some graphene, like here you can see this is the 2D material, this is the graphene, this is the single layer graphene. If you want to make it multi-layer, you can select the file, select this material, these two atoms, like this is the carbon atoms, you can select, then go to this mirror atoms, and here you can define the normal vector. For the multi-layer you can select this carbon atoms, go to the mirror atoms, and then you will find this interface. Here you can see this is the normal vector x, y, z, and then you can define this x, y, x, z, y, z, any position you can define, like this is the x, y, and then you can define the distance. You can copy this checkbox, then you can click on this apply. Here you can see mirror has been created. So for the mirror you can select the atoms, go to the mirror atoms, you can define the normal vector x, y, x, z, y, z, and then you can copy this checkbox. Also you can define the distance, copy this checkbox, then you can make the mirror. And if you want to make it centrally fit, here you can see center option is there. So you can click on this center along A, center along B, center along C. Here you can see the atom is in the center position. And again, if you want to do their study, select this simulator, go to the RESCU, Select this DFPT, density function perturbation theory. And this time you can select this Raman property calculation. You can define their parameter. Any parameter you can select as per your need and your theories. This is the damping factor, key point Cartesian, income photon polarization, outcome photon polarization, income photon wavelength, and this is the temperature in the unit of Kelvin, and this is the income photon wavelength in the unit of angstrom. So you can define the parameter. I am taking the default parameter. Then you can click on this generate file. So here you can see I have generated their input file. So if you want to run from this interface, so simply you can select this scf.input file, right click, run this option, select this run option to run this job. But if you want to run this scf.input file, dialectic.input file, phonon.input file, Raman.input file through the MATLAB command line interface, so you can open the MATLAB. You can, here you can see, and this is the graphene, and this is the RESCU DFPT folder. And here you will find this scf.input file, Raman.input file, phonon.input file, atom.input file, and this is the atom.xyz file. So here you can see this is the script for this scf.input file for this graphene, and here you can write the command, and this is the input file, scf.input file. So here you can write scf.input, and then you can run, and here you can see the calculation has been running. Here you can see the calculation has been finished. So either command line interface you can run, either interface, graphical user interface you can run. So here you can see the SCF input file has been finished. Similarly, you can select this dialectic.input file, and then you can press the enter. Here you can see the calculation is in the running condition. All the calculation has been finished.
Hello.
And for the phone, yes.
Hello. Can you repeat how to get the result without using MATLAB? You have already explained that using Origin or other tools we can plot the graph. So again, can you repeat that? How to plot without MATLAB output result?
Yes, yes. Like here you can see any folder you can select, like this is the boron nitride. So you can click on this simulator, select this RESCU. This is the DFT and this is the DFPT. So this is the DFPT. You can select any parameter and you can generate their input file. Once you generate their input file, you can run their scf.input file first. Then you can run local density of state.input file, band structure.input files. Once you run the simulation, their output file will be generated. Here you can see this is the RESCU log.output file. Right click, select this open containing folder, and then you will find the project. Here you can see this is the project, boron nitride RESCU result folder, and here you can see this is the result folder. And all the data is there. So either you can import in MATLAB, Origin, any third-party software, you can import this data and you can plot your graph. Because I have MATLAB, so here you can see this is the .mat file, and this is the density, real space density, density of state, local density of state, real space potential with different combination. You can plot their graph in Origin, MATLAB, any third-party software. You can import this graph and data, and you can plot their graph. I hope your doubt has been cleared.
Excuse me, sir. Sir,
Yes, ma'am.
what about the dielectric properties and optical inputs, sir, for this to run in Origin?
Ma'am, input file you can run in this RESCU or numerical file.
Okay, sir. For boron nitrate, it in rescue result there is no dielectric properties, dielectric input or
This
Raman
is
input like
this.
that, optical
Yes, ma'am.
properties. How
This
can we
calculation
run?
is for the density function theory, and this
Okay,
calculation is related with the density function perturbation theory.
okay. Oh, DFPT in DFPT we get Raman and dielectric inputs. Huh?
Yes. Here you can see
Okay.
simulator RESCU.
Okay.
This is the DFT and this is the DFPT. In the DFPT, you can
Okay.
see Raman property, optical phonon structure, phonon density of state is there.
Okay, sir. Okay, sir. In DFPT, we have that. Okay. We have to
Yes,
choose
ma'am.
based on the need, whether we need
Yes, ma'am.
SCSE or DFPT.
Yes.
We can plot in origin, sir, by using this result.
Yes, ma'am.
Okay, sir. But in origin, we don't have that spin up, spin down like that. No. You are showing that graph with the spin, no? Up,
Yes,
spin,
ma'am.
down, spin. Yes. For that, what we have to do, sir, in origin? In analysis plot, you are showing that spin up, spin down.
Yes, ma'am. Yes, ma'am.
Plot.
Once again.
If we are using the origin, how can we see that graph and interpret? So, is it possible in origin? If we
I
draw
need
the
to check
graph, in
whether it is possible spin up, spin down or not, because I did not use any terms in the origin. I working on the MATLAB and this interface. So
okay,
I need
sir.
to check whether it is possible or not.
No,
Then
no,
I will confirm.
we don't have origin MATLAB. That's why I'm asking. I'm using origin alone to interpret the results, to draw and interpret. That's why I'm asking, sir.
Okay,
Is there
fine.
any solution for that? If it is, please convey it, sir.
I will check. Then I will confirm to you.
Okay, sir. Thank you.
In the MATLAB, you can see this is the dielectric input calculation has been finished. So similarly, if you want to run this phonon.input file, so again you can write this command and then you can press the enter and then it will start the calculation. Here you can see the phonon input calculation has been finished. Again you need to run this Raman.input file. So you can write this command and then you press the enter. Then it will start the calculation. And for plotting the graph, you can write this command. Here you can see this is the Raman.mat file.
Sir, there is an error which says that unrecognized variable rescue.
Yes, ma'am.
Error is popping up which says unrecognized variable rescue.
On your system, ma'am, you are
Yes.
getting the error on your system.
Huh.
Can you send the screenshot on the
Okay.
WhatsApp group so that I can check? So here you can add this command for plotting the Raman.mat file. And here you can see, then you will find this graph. You can see this is the Raman polarized. And this is the Raman polarized and Raman intensity, and this is the Raman shift for this graphene bilayer structure. Here you can see this is the maximum peak and this is the minimum peak. And this is the averaged Raman spectrum, Raman intensities, and this is the Raman shift. Peak value, minimum peak value, and this is the maximum peak value. So I have shown you the multiple proper. So I have shown you the maximum features of this software. So if anyone has any more query related to this software, so kindly you can unmute your mic and ask me the query, whatever query you have. Then I will try to help you. And in tomorrow session, my colleague and me also, will cover the more property of this rescue. And in the simulator, you can see this is the numerical. So tomorrow's session is based on this numerical for the density function theory and non-equilibrium green function theory, where you can simulate your device structure, molecule structure, crystal structure. So up to 6 probe device structure you can simulate through this nanodical software. In the build option you can see, and this is the device maker. Here you can see this is the left right structure, left center right structure, bottom top structure, bottom center top structure, front and back structure, front center back structure. So this 6 probe device structure you can easily simulate through this nanodical software. So if anyone has any queries, so kindly unmute your mic, or you can drop the message on the chat box so that I will try to help you. Here you can see I have created some project related to this rescue software. So I can show you the feature once again. Here you can see this is the diamond crystal structure, and I have calculated their phonon band structure, phonon density of state. Here you can see this is the phonon band structure for the diamond crystal structure. This is the phonon band structure, and this is the structure. Here you can see, and this is the structure, and this is the phonon density of state. And also relaxation is also possible if you want to optimize your structure. So here you can see this is the graphene, and if you want to optimize this structure, I need to copy this project. Then go to the simulator, select this rescue, then go to the relaxation. And here you can see this is the basic settings for this relaxation. And here you can see this is the relaxation method, Quasi-Newton, steepest descent, consequent gradient. So any method you can select, you can generate their input file. This is the spintronics basic settings. So you can generate their input file. Here you can see this is the relax.input file. And similarly, you can select this file, right click, select this run option to run this job. And once this calculation will finished, then you will find this atom relax.xyz file. Here you can see the calculation is in the running condition. And once this calculation finished, then you will find the optimized structure.
Sir,
Yes, ma'am.
hello. On looking at the input and output file, it seems that the results by default are getting saved in the .mat and .h5 format. That is MATLAB and H5 format. So there is, I'm looking at the dielectric and optical results and phonon also. There is no text file for that. There is only MATLAB and H5 type of file.
Like here you can see, and this is the dielectric.input file, phonon.input file. So we are running only the optical input file because it will take the output from this SCF dielectric phonon.input file. Then it will calculate the optical property. In the optical property input file, you can see it will take the output from this SCF.mat file, dielectric and phonon. Here you can see it will take the output from this file, and for their output, here you can see this is the input file, and in the result you can see this is the optic.mat file, this is the output file, this is the phonon.mat file.
Yeah, exactly. Can we do something that the output is written in a text file and not in a .mat or .h5 type of file? Because these types of files we are not able to open without MATLAB. And there is an error of in MATLAB when I open there is an error which is unrecognized function or variable rescue.
So for the running the simulation in the MATLAB, first you need to do the installation on the MATLAB as well. Then you
Oh,
can do
I have
the
done.
simulation
I
because you
have
have not. Yes,
okay. I have installed MATLAB. I have shared the picture of the screen on the WhatsApp group also, where the
ma'am.
error. Yes. Hello.
Yes, ma'am. Ma'am, you did not do the installation on the MATLAB as well because here you can see I have already done the installation on the MATLAB as well.
Installation on the MATLAB.
Yes,
Uh,
and it will take the max GCC for the Linux and one second
okay.
and MinGW64 for this RESCU and nanodical. So if you have Linux like MATLAB, then go to the add-ons
Wait a second. Add-ons, as in home, then add-ons.
and
Okay.
yes, here you can search for the compiler MinGW.
Get add-ons.
Yes, MinGW.
MinGW.
Here you can see this is the MATLAB support for MinGW compiler, and this
Search.
compiler you need, yes, and this compiler you need to download. Then you can do the installation of this rescue either nanodical in the MATLAB. Then you can do the simulation. Until and unless you did not do the installation on the MATLAB, then you did not do the simulation.
Okay, now I got it. So MinGW, if I install, this problem will go away.
Here you can see once again. I can show you the procedure. Here you can see. Choose GCC for the Linux and LCC Win32 for the 32-bit MS Windows. And if you have 64-bit, then you need to install this MinGW W64 compiler. So you need to do the installation on the MATLAB as well. Then you can simulate this structure from this MATLAB. So for any query, kindly you can unmute your mic or you can drop the message on the chat box so that I will help you. And here you can see the relaxation calculation has been finished. And here you will find this relaxed structure.xyz file.
Sir,
Yes, ma'am.
sir, can you show me how to construct the BAM structure? Barium, magnesium, aluminate.
Any material you can select like this
Sir,
is
up
the
till now
items.
we are selecting only from the online or from the desktop. But if we have to prepare our own structure, then how to do it?
Yes, ma'am. Then you can select this file option, go to the new option and select this crystal option. So if you want to make the crystal, then you can select file, new, then crystal. Either you can select build, then you will find this crystal. And you can define their space group, and according to space group, the previous lattice will automatically selected. You can define their ABC value as per your need, alpha, beta, gamma value. You can add the element through this plus option. N number of atoms you can add, and then you can show the primitive cells, conventional cells, then you can preview, then you can build. So any complex structure, simpler structure, alloy, any structure you can create through this crystal builder. Or if you want to make a molecular structure, so here in the build option you can see this is the molecule 3D builder, this is the molecule 2D builder. Like this is the molecule 2D builder. Any fragmentation you can select, like this fragmentation I would like to select. And if you want to draw the single bond, like this is the single bond. So any complex structure you can create, and then you can simply click on this add data. Here you can see single bond, double bond, triple bond. If you want to change with double bond, here you can see this is the double bond. And if you want to add more fragmentation here, so any complex structure you can design, then you can click on this apply data. Then in a very quick time you can show their like atom position, atomic position, and for the band structure simulator, select this RESCU. Either you can select this SCF calculation or you can select this density function perturbation theory. So anyone you can select, like this is the DFT. You can define first, you can define their SCF input. You can generate their input file. Here you can see the SCF.input file has been generated. First you need to run this. Yes.
Sir, during calculation we have to only use default values.
No ma'am, as per your need you can define the parameter. So you can visit our website what the parameter you need to define. I am taking the default parameters. You don't need, like here you can see this is the what the value you can add. So whenever you get the time, so you can visit our website and then you will find the more theory documentation is also there. And you can define their generate their SCF.input file. So first you need to run the SCF.input file, then go to the simulator, select this RESCU, go to the analysis, and you can define this band structure. Here you can see this is the symmetry K point, and this is the number of K point. You can click on this generate file. So this is the band structure .input files. Once this SCF.input file will be finished, you can run this band structure .input file. Then this calculation will finished, then their output will definitely plotted. And here you can see this is the force field calculation. If you want to apply force field, UFF, ZFF, any force field calculation you can select, and you can study their properties. So from my side, thank you to all of you for joining this session.